Welcome to This Explainer. I'm absolutely thrilled to have you here today. We've got a really exciting mission ahead of us. We're going to untangle three commonly confused science terms by exploring the invisible world of moving particles. You hear the words temperature, thermal energy, and heat all the time in everyday life, right? But in physics, they have very specific, very distinct meanings. By the end of this session, you're going to know exactly how they differ and how they all connect to the microscopic motion happening all around us.
So, here's our quick roadmap for today. First, we'll hit particles and kinetic energy. Next, it's temperature versus thermal energy, followed by heat, which is literally energy on the move. Then, we've got a couple of pause checks, a concise recap, and finally, we'll wrap up with the transfer question.
All right, Section 1, Particles and Kinetic Energy. Let's dive right into this.
When we talk about energy in physics, we're usually talking about mechanical energy, right? And one of the most important forms is kinetic energy, literally the energy of motion. Picture a roller coaster plunging down a huge drop or, a skater gliding across a skate park. Because that skater has mass and is moving with a certain velocity, they have kinetic energy. It's a macroscopic concept. You can see it with your own eyes. Basically, if an object is moving, it's got kinetic energy.
But to really grasp thermal physics, we gotta shrink down. I mean, way, way down. You see, even when an object looks perfectly still to us, like the desk you're sitting at or a glass of water, the invisible atoms and molecules inside that substance are constantly moving. They're vibrating and colliding into each other nonstop. And because these tiny microscopic particles are constantly in motion, well, they also possess kinetic energy. This invisible microscopic motion is literally the engine driving our next two concepts. Which brings us to Section 2, Temperature versus Thermal Energy.
Let's start with temperature. Temperature is strictly a measure of the average speed, or the average kinetic energy, of those microscopic particles we just talked about. If you heat something up, its internal kinetic energy goes up, meaning the particles are moving faster on average. Cool it down, they move slower. The absolute most crucial thing to remember here is that temperature is completely independent of the object's total mass. It only cares about the average.
Now, what's really interesting about this next concept is how it contrasts with temperature. Thermal energy looks at the total internal kinetic energy of a substance, and because it's a total, the number of particles, which is just the mass of the substance, matters immensely.
Let's put them head-to-head to really see the difference. Temperature is average kinetic energy, so mass doesn't matter. But thermal energy is total kinetic energy, meaning mass absolutely matters. To picture this, just imagine a small cup of boiling water and a gigantic iceberg. The boiling water has a much higher temperature because its molecules are zipping around incredibly fast on average. But get this, that massive iceberg actually contains way more total thermal energy. Crazy, right? But think about it. Even though the iceberg's particles are moving slowly, there are just so incredibly many of them due to its enormous mass. The sum total of all that tiny motion adds up to a massive amount of thermal energy.
Moving right along to Section 3, Heat, Energy on the Move.
So we've got these pools of thermal energy everywhere. But thermal energy doesn't just sit in one place. It naturally flows. And the crucial point is that in physics, heat is actually an action word. Heat is the literal transfer of energy, and it's driven strictly by a temperature difference. If you bring two objects of different temperatures together, energy is transferred from the hotter object to the colder object. And this keeps happening until both objects hit the exact same temperature, a state where there's no longer any net heat transfer.
This transfer actually happens in three specific ways: conduction, convection, and radiation. And honestly, sometimes they all happen at the exact same time. Just think of a roaring fireplace. If you touch a hot metal poker that's been in the flames, you feel heat through conduction, which is direct physical contact. The hot air rising up the chimney, that's convection, the movement of a fluid driven by buoyancy. And that nice warmth you feel on your face when you're standing a few feet away, that's radiation, where heat is transferred through invisible electromagnetic waves without needing any medium at all.
And this brilliantly illustrates how we calculate that exact transfer of heat, using an equation represented by the letter Q. So Q equals mc delta T. This just shows us that the amount of heat transferred relies on three things: the mass of the substance, how much its temperature changes, and its specific heat. Specific heat is a unique physical property for every single material. It basically tells us how much heat is required to change the temperature of 1 kilogram of that substance by 1 degree Celsius. For example, water has a super high specific heat. That means it takes a whole lot of energy to change its temperature compared to something like a metal, say aluminum.
All right, Section 4, pause checks. Let's see what we've learned.
We've covered some fantastic ground so far.
Now I want to actively test your comprehension with a quick scenario check. Here is your first question. When two bodies of different temperatures are brought into contact, what is the overall direction of heat transfer? Take a quick beat to think about it.
Okay, if you said from the higher temperature object to the lower temperature object, you absolutely nailed it. The reasoning here is microscopic. When those two bodies touch, their particles collide. The faster-moving particles from the hot object literally bump into the slower-moving particles of the cold object, transferring their kinetic energy. This cascade of microscopic collisions moves energy from hot to cold until everything balances out.
Let's try one more. True or false? The kinetic energy increase of a falling object acted on only by gravity is equal to its weight multiplied by the distance it falls. Think back to the work-energy theorem and how mechanical energy transforms.
And the answer is true. When you hold a rock up in the air, it has gravitational potential energy, which is just mass times gravity times height. And weight is just mass times gravity. So as that rock falls, gravity does work on it over that distance, successfully converting that stored potential energy directly into kinetic energy. It's a beautiful example of the conservation of energy in a closed system.
Excellent work on those. Let's transition into Section 5, Concise Recap.
Let's lock in these key takeaways before our final challenge. Here is exactly what you need to remember. First, on a microscopic level, particles are always moving. They always have kinetic energy. Second, temperature is strictly a measure of the average kinetic energy of those particles. Third, thermal energy is the total kinetic energy, meaning the mass or the sheer number of particles makes a huge difference. And finally, heat is an action. It's the actual energy transferred between objects because of a difference in temperature.
And finally, Section 6, the transfer question.
Let's see how all of this builds into our final challenge today. I'm going to present a real-world scenario drawn straight from a specific heat lab. Here it is. Soil has an approximate specific heat of 800 joules per kilogram degree Celsius. But water-specific heat is way higher, at 4,186 joules per kilogram degree Celsius. So as winter sets in and freezing weather arrives, which one is going to cool down and reach 0 degrees Celsius first? The farmer's soil field or a nearby water pond? Think about what specific heat really tells us about how a substance gains and loses thermal energy. I'm going to leave you to ponder that puzzle. Thank you so much for joining me on this explainer today, and hey, keep asking questions about the amazing physics happening all around you.